All right, so we've all seen this, right? AI is getting insanely good at making 2D images. You type in a few words, and boom, you get a masterpiece. But what about 3D? Creating clean, sharp, actually usable 3D models. Well, that's been a much tougher nut to crack. For a long time, AI-generated 3D objects have been kind of, well, blobby. But this new approach, BSP-Net, it's completely changing the game by teaching AI to think less like a painter and a whole lot more like a sculptor.
And yeah, this image just says it all. Look at the left. That's the BSP-Net model. See how clean those lines are? How efficient it looks. It feels like something a human artist would actually make. Now look at the right. That's from another top-tier method called ImNet. It's just messy. It's what we call over-tessellated, which is a fancy way of saying it's made of way too many tiny triangles. It totally loses those sharp defined edges we need. It's detailed, sure, but it's a structural mess.
So the big question is, how did they pull this off? How in the world did they get an AI to finally see and create those clean, sharp edges that are so critical for good 3D models? Well, the answer, it's actually really clever and surprisingly elegant. But before we get to the solution, we kind of have to understand the problem itself. Like, why was this so hard in the first place? It really all comes down to the old ways AI tried to build 3D shapes. So, for a while, a lot of models used voxels. Think of them like tiny Lego bricks in 3D space. To get any real detail, you need millions and millions of them. It was just super inefficient. Then, newer methods came along using what are called implicit functions. Imagine defining a shape not as a solid thing, but as a kind of continuous fog in space. To turn that fog into a solid object, you have to run this complicated process to find the surface inside it. And in doing that, you'd usually smooth out all the nice, sharp details you wanted to preserve in the first place.
Okay, so the big breakthrough here didn't actually come from some brand new wild AI idea. Nope. The researchers went back in time a bit and dusted off a classic, time-tested concept from the world of computer graphics.
It's called binary space partitioning, or BSP for short. And I know, that sounds super technical, but don't worry, the concept is actually incredibly simple and powerful. Imagine you have a big block of clay. Instead of adding little bits of clay to it, you take a series of cookie cutters, or in this case, flat planes, and you just carve into it. Each cut defines a simple, solid piece. Then you just combine those pieces to build your final complex object. It's all about subtraction, not addition. And this is exactly what it looks like in practice. At the top, you've got these simple planes that are just slicing up space. Then, in the middle, the network figures out how to group those planes together to make simple, solid shapes. You see the square and triangle there? And then, boom, at the bottom, it assembles those simple pieces into the final, more complex object. The big idea here is that the shape is constructed from these solid geometric building blocks. Okay, so that's a really cool idea in theory, right? But how do you actually teach a neural network to do this? I mean, how does it know which planes to predict in the first place, or how to stick them all together? Well, the researchers were smart about it. They broke the problem down into 3 main steps. Step 1, the network looks at some kind of input, say an image, and it just predicts a whole bunch of planes. Step 2, it figures out which of those planes to group together to make those simple, solid building blocks. And finally, step 3, it learns how to put all those blocks together to create the final shape. Simple as that. Now, you might be thinking, that still sounds pretty hard. And you'd be right. Trying to teach a network to get this perfect right from the get-go is super difficult. The decisions are very yes or no, all or nothing. And neural nets aren't great with that. So they came up with this really clever 2-stage training plan to make it all manageable. So in stage 1, they basically let the network make soft decisions. You can think of it like creating a rough draft or a sketch. The network gets the overall shape right, the general placement of all the parts. But if you look closely, the edges are kind of fuzzy, there are little imperfections. It's a continuous approximation, which is just way easier for the network to learn at first. Then you get to stage 2. This is where the magic happens. The network takes that rough draft and just locks everything into place. It starts making hard decisions, fine-tuning the exact placement of every single plane. This is the sharpening phase. It cleans up all those fuzzy edges from stage 1 and spits out a perfect, super precise model. So, the big question is, does this whole 2-stage sculpting thing actually work? Oh yeah, the results are, well, they're pretty staggering. I mean, just look at this head-to-head comparison. On the left, that's the chair made by BSP-Net. On the right, that's the one from ImNet, which is a really good state-of-the-art method. From far away, you might think, they look kind of similar. But just zoom in on that chair leg. The BSP-Net model is so crisp, so geometric. The IM-Net model, it's just a lumpy, smoothed-out blob. It's not even a contest, really. And the numbers absolutely back this up. So this table compares BSP-Net to a super high-res version of IM-Net. Okay, so visual quality, they're pretty close. But check out sharpness, where a lower score is better. BSP-Net is more than 3 times sharper. But here's the absolute kicker. Look at the number of polygons. IM-Net is using almost 83,000 polygons to make that lumpy chair. And BSP-Net, just 655. That's insane.
Yeah, you heard that right. That is not a typo. On average, we're talking about models that are just as good, but made with over 100 times fewer polygons. This is just a massive, massive leap in efficiency. It means the models are way smaller, they're faster to render, and they're so much easier for actual artists to work with. But wait, it gets even cooler, because the AI is building these objects from component parts, from these little solid shapes. Something amazing happens. It starts to develop a kind of understanding of the object's structure. Nobody ever told it what a chair leg or a seat is. It just figured it out, naturally grouping its building blocks into these parts that actually make sense to us. And this isn't a one-off thing. This understanding is consistent. Just look at these different airplanes. Even though they're all different models, the AI has used the same colors for the same parts on every single one. The fuselage is cyan, the wings are green and yellow, the tail is blue and magenta. It has learned a consistent blueprint for what an airplane is. This is a huge step. We're moving from AI that just copies things to an AI that might actually understand them. So, where do we go from here? What does all this mean for the future of making 3D stuff with AI? Well, it's definitely a game changer, but like any brand new tech, it's not quite perfect yet. And the researchers are totally open about the current limitations. For one, because it works by combining solid pieces, it has a tough time with things that are naturally hollow, like, say, a teacup. The training also takes a long time. We're talking up to 6 days for a really complex model. And, one last thing, the network uses the same number of planes for every object, whether it's a simple box or a complicated chair, which isn't ideal. But even with those challenges, the potential here is just enormous. The incredible efficiency and quality of these models could completely change how we create assets for things like video games. Just imagine being able to generate thousands of unique, game-ready items, chairs, cars, whatever, in minutes instead of months. This could massively speed up how we build games, simulations, and all sorts of virtual worlds. And that leaves us with one last really big question to chew on. We've just seen an AI that can not only build 3D objects, but seems to be starting to understand their structure. So once this technology really gets going, what are we going to ask it to design? New styles of architecture? More efficient machine parts? Or maybe something completely new, something we can't even imagine right now? The possibilities are just wide open.